All right, everyone, welcome to the second day session of the conference on fixed point theory and application. So our first speaker for today's session is Dr. Irga Abebe Belai from Narswan University, Thailand. The title of his talk is Solution of Perturbed Krasno
Translate.
Krasnoselki man iteration and their applications to image restoration problems. You can correct me, Dr. Irga, on the title.
Uh, okay, maybe I think there is some change because you
Oh,
started something like perturbed, right?
yes.
On my slide, I just prepared it solutions of perturbed. So there is a change,
Oh,
I think.
all right, no problem. Some minor
Okay,
change. You will send an email or I will update that one. So you can just continue, start your talk.
okay. Thank you. My name is Yirka. I am a postdoctoral student at Naresuan University, Thailand. So today I will be talking on fixed point related topic titled with solutions of perturbed Krasnoster schema iterations and their applications to image restoration problem. So this work is like a joint work. We have other contributors. Professor Rabian from Nareswan University is the leader of the research team, and we have also other members. So okay, this is the outline of my presentation. It consists of introduction, some literatures, application part, and finally the conclusion. So for the theory, we did it on Hilbert spaces. So we know what Hilbert space are and the definition of fixed point as we are going to use them later. And some definitions regarding the mappings like non-expansive mapping, a mapping which satisfies the inequality in one, causing an expansive mapping, monotone mapping, and others like strict non-expansive mappings. So this will be used later. So what are fixed points? Actually, before it has already been defined here. A fixed point, a point in H is said to be a fixed point of a mapping T if it is unchanged or if it remains unchanged under the mapping T. So fixed point has got many applications like in economics, physics, engineering, and so on. But in reality, in practice, if we have nonlinear mappings, the fixed points, we cannot easily find fixed points of complex nonlinear mappings. So in that case, what we do is just we approximation. So many approximations have been done in this regard. Particularly, there have been many iterative methods involving non-expansive and quasi-non-expansive mappings, like in Ilderstein, Artwang, and Inwa. One of the oldest and famous.
Dr. Irga, if you don't mind,
Yes,
can you just um, on your video?
my video.
Yes, it's off.
Okay, let me. So I cannot find it.
So on the audio or
Let
there's
me.
audio, there's video, you can make it on or just check your camera.
Maybe let me. Let me check.
Okay, let us continue.
On my side, it's functioning well.
Oh, his camera?
Okay. Okay.
Let him continue this way, and
Yes.
later you open it. Yeah.
All right. Yeah, continue, Dr.
Dr.
Yuka.
Yuka, you can continue.
Okay.
We can see your presentation, no problem.
I cannot
Okay.
open. Now I can. I can now.
Yes, thank you.
Yeah, now we see you. Yeah. Mhm.
Okay.
So, you are on page.
I was here.
Okay, yeah, make it at the
Can-
presented mode slide. Okay. Yes, continue.
Okay.
Thank
So
you.
one of the most famous iteratives for non-expansive mappings is the Krasnow-Cell schema iteration, given by iteration number 4. So this has got many applications actually in convex optimization, image processing, and inverse problems. So for this reason, many researchers have been working on this area. One of them is Moalen, which introduced algorithm number 5, and they proved the strong convergence of the sequence generated by 5 to a fixed point of the sequence. I mean the mapping. But in this case, the underlying mapping is quasi-contraction mapping, which is a very small class of mappings. So this has been improved in the later, like in the Gabriel Georgis. They improved it to non-expansive mappings. Actually, they they developed the algorithm given by SAGE. So in this case, they also obtained strong convergence of the given the sequence to the mapping T. And very recently, Cortil and Poipocot proposed a perturb. In this case, they tried to perturb the iterations, like they have added some perturbation parameters to each step, and they tried to study the convergence analysis of the sequence. So in this case, they proved the strong convergence, but the parameters were restricted to be in L1. On top of that, the mapping was required to be quasi-contractive, which is still restrictive condition. So our aim is just to extend the restrictive conditions in the, especially in the pickpocket, which means in this one. So what we did was these are the assumptions that we used, and this is our algorithm. We proposed this algorithm here. These perturbation parameters are not necessarily in L1. We have somewhat relaxed them to be to satisfy the condition in C5. So this is more relaxed property. And the mapping is not required to be in the strict contractive and so on, like the previous ones. Here it is quasi non-expansive, which is more general. So these are some of the improvements we have made here. So we proved the strong convergence of the sequence generated by the algorithm in 9, actually, 8 to 9. Before proving the strong convergence of the method, we just proved boundedness of the sequence, and using this boundedness property together with some preliminary lemmas, we proved that the sequence UN converges strongly to a fixed point of the given mapping, the quasi non-expansive mapping, which is with the property, this property, which is the projection of the arbitrary constant u bar to the set of fixed points of the given mapping. So here we have an example, actually, just to clarify that we have mappings which are quasi non-expansive and not non-expansive. So this mapping is quasi non-expansive. This is like we have shown that it is not non-expansive. So this mapping is a mapping which is quasi non-expansive. That's not non-expansive. So together with these parameters, which are required by the conditions 1 to 5 of the previous theorem, these parameters satisfy the conditions of the theorem, and together with the quasi non-expansiveness of the mapping. So we conducted an experiment just to show the convergence. Here we have the notation En. It was a sequence of the error terms. You see, this Un is a sequence, the iteration, and P star is a fixed point. It was 0. We have 0 as a fixed point of the mapping. So here, just to show that, to compare the non-inertial and inertial aspects of the algorithm. So here the red one represents for the inertial and the blue one for the non-inertial version. And another visualization is for the perturbed and non-perturbed, which means if we take the perturbation parameters, all the perturbation parameters to be 0, the convergence becomes a bit faster. Like we can see here, the red one is for the non-perturbed one, taking the perturbation parameters to be 0. Here, the blue one is where all the perturbation parameters are non-zero. So it can show us like the non-perturbed version is more faster, actually. But in order to compare with the other results in the literature, we have taken another mapping. Here, Tx equal to x over 2, which is contraction mapping, actually. The reason why we took contraction mapping here is because of this Georgis and Cortil, they used a contraction mapping. So in order to compare the methods, we need to take the same type of mapping and see the differences. So this is the result, the visualization, comparing all 4 methods. These are the names of the algorithms. CK algorithm is like for GK is for Georgis and Kumam. CP is for Cortil and Perpetuate. Algorithm 3.1 stands for the proposed algorithm here. So it shows something with better performance from the visualization. So these are the results we found regarding the theoretical aspect. When it comes to application, we try to apply it in image restoration. Actually, this is just simulation. I mean, when we try to restore images, it's not easy. We need to know the blurs and the actual images we should get from the capture. But here, what we do is we take some clear pictures. I will talk about that later. So what is a blurred image? I mean, blurred image. It's an image that is less sharp and not clean. So because of many things, it may be less sharp and not clean. So how can we blur an image? Because of many reasons. Maybe it is because of camera shake. maybe the object whose picture is going to be taken is moving, or the lens is not focused, and other environmental conditions. So because of this, we may obtain blurred images. Here we have, we take original clean image U in R n times 1 actually, and the corresponding blurred image is represented by nu in Rn times 1. The concept of image deblurring is just restoring the original image U from the degraded image nu. So in this case, in the practical applications, what we have is a blurred image nu. We don't know about the clean image U. We don't know about the type of blur images, blurring operators. So we are required to find the clean image from the degraded or the blurred image nu. But in practice, this is very difficult. That's why we just try to simulate and compare the performance of the algorithms discussed earlier in restoring images or clean images. So here they are related by this inverse problem. The degraded image nu is given as like h times u plus omega. Here h is a blur operator and u is a clean image. Omega is some external noise actually. So here, in order to solve this problem, in order to solve the image restoration problem, we are supposed to solve this minimization problem. Excuse me. So solving the image restoration problem means just solving this minimization problem over U. Like U is supposed to be the clean image. And after some transformations, this 11 is the same as monotone inclusion problem, solving monotone inclusion problem with taking this F and G to be the terms in 11. So from this, if we take F to be grad small f and capital G to be the subdifferential of small g, we have this grad F is monotone, we know this, and subgradient of G is maximally monotone. So solving this monotone inclusion problem will be later converted to this fixed point problem. Here is the main point actually. Solving the monotone inclusion problem, the right-hand side of 13 is equivalent to solving the fixed point problem on the left-hand side of 13. So like we are in a position to apply the fixed point problem to restoring the image. So instead of solving this monotone inclusion problem, we will solve this fixed point problem. And this, we will take this mapping TRN. TRN will be taken in our algorithm. This mapping is proved to be a non-expansive mapping. So using this mapping, we solve the fixed point problem. We substitute this mapping in the algorithm and solve the problem. But for this one, what we do is we take a clean image, not only one image, two images. Here we have for the mandrill and butterfly images. Then we apply blur operators, known blur operators. You see, now we have taken known blur operators because we are just checking the efficiency or the performance of the methods or comparing the performance of the methods. Like I told you earlier, the real practical image restoration problem is just finding the clean image from the degraded image, but that one is not easy, and it's still under study. So finally, we will recover the resulting blurred image using the algorithm. So here, what we do is we have here, let me talk about this one. We have different types of blurs: average blur, disk blur, Gaussian blur, and motion blur. So for the first one is here, the original mandrel image is given in subfigure A of figure 4, and the degraded version of it given in B. So I'm not sure if you can identify the difference between the two images. The right-hand side, or image B, is a degraded one. So the idea is just use the algorithm and restore the degraded image. So here we have the restored image using the 3 algorithms in the 3 methods. This one is using algorithm 1. Actually, it is algorithm 3.1 in this paper. The image in B is the algorithm, the image restored by GK algorithm, and the third one is the image restored by the Moellen and Moellen algorithm. So can you see the difference, please? Can you identify some differences between the the images?
Yes, yeah, we can identify, yeah.
Yeah. For me, I can see a small difference. The image restored by algorithm 3.1 looks somewhat better for me. Similarly, here for the butterfly, we have just imposed the disk blur, and these ones are the restored images. Similarly, the first one is the image restored using the first algorithm, the algorithm in this paper. The second one is the image restored using GK algorithm, and the third one is for the MFP algorithm. So there is slight difference actually, but it's not easy to conclude this one is better than this one. So we need to do something, or we have to quantify the difference. So in order to measure the differences, we employ 2 metrics here. The metrics are, one is ISNR method, and metric, and the second one is the SSIM, which are given by the formulas in 14 and 15. So we have many parameters here actually. So using this matrix, we compared the performance of the methods. So here, the beta, the ISNR indicates the best recovery or the best algorithm. That's how we compare the performance of the methods. For the SSIM, it ranges between -1 and 1. The value of SSIM, which is close to 1, indicates the better performance actually. The value which is close to -1, it shows opposite images which are not related. So based on this, we have for the 4 types of blurs, we obtain these results in table 1. So these ones are, the first column shows the types of blurs, and this second column with its subcolumns shows the ISNR and SSIM values. Similarly for the GK algorithm and MFP algorithm. So if you see, for example, in the first column, or the ISNR for the proposed algorithm, here, we have ISNR value of 4.45. But for the GK algorithm, here we have 1.8. For the MFP, we have 2.7 something. Similarly, we see that the ISNR values for the algorithm 3.1 are relatively better than the others. And for the SSIM, you can also see the values of the SSIM. So here, slightly better performance. Again, we have also taken only one blur operator, the motion blur. Just to compare actually how the algorithms behave when the value of L, the motion blur, changes. So as the length of the motion increases, the performance of the methods reduce. That's what we see from here. But still, algorithm 3.1 still maintains its outperformance over the GK and MFP algorithm. This is what we observed. So coming to the conclusion, we introduced an inertial approach for approximating the Krasnow-Saleski-Mann iteration. And we discussed strong convergence of the method. We employed it in just to compare how it performs in restoring blurred images. So it shows that it has like slightly better performance than the others. But the issue is, like I said previously, how can we identify the exact blur operator and the exact clean image, given that like from a degraded image. If we are given a degraded image, how can we identify the clean image and the blur operator? That is the issue now. So I will try to work on that. So this is all about my presentation. Thank you so much.
All right. Thank you so much, Dr. Irga, for the nice presentation. Let us thank our speaker. You can.
Thank you so much for the nice presentation, Dr. Ika.